In this presentation, we will talk about suspension Anosov flows and Birkhoff sections. Given a non-singular flow on a closed three manifold, a Birkhoff section is the immersion of a compact surface that is transverse to the flow lines in the interior, but is tangent to the flow lines along the boundary. Such an object provides important topological information about the dynamic and the flow itself. Our goal is to study these sections in the case of suspension Anosov flows. We will present some elements of how they are related with classification, dense surgeries, and singular affine structures on surfaces. In the first part, we present some basic definitions and a motivating question. And in the second part, we will show that in a suspension and also flow, the set of genus 1 Birkhoff sections is in bisection with some family of singular affine structures on the torus. So let's start with Anosov flows. Well, consider some closed three-manifold M. Consider a non-singular vector field X, and let's call phi t the flow generated by X. Well, we say that the flow is Anosov if its differential acting on the tangent bundle of M preserves a hyperbolic splitting. And what's a hyperbolic splitting? Well, this is a decomposition of the tangent bundle of M into three line bundles that we call ES, C, and U, where EC is just the line bundle generated by the vector field, and the dynamic is contractive along the ES bundle, which is also called the stable bundle. S is for stable, and the dynamic is expansive along the unstable bundle, the bundle EU. The classical examples of Anosov flows are the geodesic flow of a surface with negative curvature and the suspension flow associated with an Anosov diffeomorphism on the two-dimensional torus. This second example is constructed as follows. Consider an Anosov diffeomorphism on the two torus, for example, a hyperbolic linear automorphism given by a hyperbolic matrix with integral coefficients. And then consider the three manifold that is the torus T2 times the interval 0, 1. Well, if we glue the two boundary components of these three manifold using the diffeomorphism A, we obtain a closed three manifold equipped with an Anosov flow. Suspension Anosov flows are the simplest Anosov flows from many points of view. For example, they are the only ones which supports a global transverse section. There is a boundaryless surface embedded in the three manifold such that the flow can be written as the first return map to this global section. An important property of Anosov flows is the stable manifold theorem. This theorem states that the plane bundles given by EC plus ES or by EC plus EU, these plane bundles are integrable and they integrate into a pair of transverse two-dimensional foliations that intersect along the flow lines. Well, about classification of Anosov flows, let's say that um, two flows in two manifolds, M and N, are said to be orbitally equivalent if there exists a homeomorphism from M to N, which sends oriented orbit segments of the first flow onto oriented orbit segments of the second flow. And a mainly open question is to classify the different orbital equivalent classes of Anosov flows by the C1 structural stability property of hyperbolic dynamical systems or Anosov flows. We know that there are at most countably many different orbital equivalent classes, and so it makes sense to search for a finite set of computable invariants which allow to distinguish these classes. Let's explain what's a Birkhoff section. So consider a non-singular flow phi on a three-manifold M. Well, a Birkhoff section is the immersion of a compact surface in M such that along the interior of the surface, well, the surface is embedded, not just immersed, but embedded, and transfers to the flow lines. Along the boundary components of the surface are sent into a finite set of periodic orbits of the flow. The other condition is that there exists some positive time t such that the orbit segment of length t of any given point in the three manifold intersects the surface. Well, so we have some picture here of what's a Birkhoff section. So on the left, we have a surface sigma with three boundary components. Well, this surface is immersed in our three manifold. The boundary components are sent into periodic orbits of the flow, and along the interior, the flow is transverse, and there's a the flow is transverse along the interior. Okay, so here on the right we have a local picture of how does it look like the immersion of this surface near a boundary component. This is some kind of helicoidal surface spanning around the periodic orbit. Well, the first consequence of the previous definition is that there's a well-defined first return map, first return homeomorphism, if you want, on the interior of the Birkhoff section. It is not defined along the boundary components of the section, but there's an operation that we can do that is called the blowdown operation, and it consists in collapsing the three boundary components of the surface sigma, producing in this way a closed surface, sigma hat. And well, the first return map on the interior passes down to the quotient, and we have a map P hat that's called the blowdown map associated with the Birkhoff section. And in the Anosov case, it can be seen that this map is a pseudo-Anosov map. Okay, and this is basically because the stable and unstable manifolds of the flow, when intersect the boundary, the interior of this surface, it determines two invariant folations which are contracted and expanded by the first return map. Associated with a Birkhoff section, there's a set of parameters. we can think that we have the a surface sigma hat here on the left. We take a finite set of points in this surface, then we blow up the surface along these points, creating in this way a surface sigma with three boundary components, or with some boundary components, sorry. And then we embed this surface on the three manifold M. The embedding along each boundary component, in a neighborhood of each boundary component, can be described with two parameters that are called the linking number and the multiplicity, which are essentially the number of turns that the surface makes around meridian and longitude coordinates. Okay, so the parameters associated with a Birkhoff sections is the data of a closed surface sigma hat, a pseudo-Anosov homeomorphism on this surface, a finite set of periodic orbits of the pseudo-Anosov, which are the points that we are going to use to blow up, and some integral coordinates associated with the embedding on the boundary. Okay, and the genus of this surface is not necessarily one. So these pseudo-Anosov homeomorphisms will have singularities in the case of greater genus. Well, let's say that Anosov flows, the world of Anosov flows in three manifolds is divided into the transitive and the non-transitive ones. Let's say that a flow is transitive if there exists a dense orbit on the three manifold. And the main connection of Birkhoff sections with Anosov flows is given by the following theorem. Um, every transitive Anosov flow on a closed three manifold admits at least one Birkhoff section. This theorem was originally proved by Fried, and then it was generalized to any transitive expansive flow by Marco Brunella. And well, the existence of such a section has serious implications about the topology of the flow and the three manifold that supports the flow. In particular, um, we are interested in the following question, or there's the following question. Given two Birkhoff sections for any two Anosov flows, so consider we have two Anosov flows VTI in a three manifold MI, and for each flow we have a Birkhoff section. That is the data of a compact surface, a pseudo-Anosov homeomorphism, and some finite set of periodic orbits that we will use to blow up, and some finite set of integers associated with the embedding on the boundary. So consider we have two Birkhoff sections associated with two abstract Anosov flows. So can we decide if these flows are orbitally equivalent just by looking at the information on the Birkhoff section? Um, well, so maybe the first question, or the first problem that we have to address is uh, the following, the result given in this theorem. So in the case of Anosov flows, every Birkhoff section determines a unique orbital equivalent class. Okay, the orbital equivalent class of the flow associated with each Birkhoff section is uniquely determined. This theorem is a very natural theorem, but the proof is not so direct. There are some technical issues related with the proof of this theorem, but we can count on this as something that is true. We want to remark as well that there exists some classification invariants for pseudo-Anosov homeomorphisms on closed surfaces. For example, the theory of train tracks, mainly due to Handel and Thurston, or the theory of the geometric type due to Bonatti and Langevin. And well, since transitive Anosov flows are constructed by um, suspending pseudo-Anosov homeomorphisms and blowing up periodic orbits, we can hope to use these classification invariants of pseudo-Anosov homeomorphisms to produce classification invariants of the Anosov flow. So it is in this sense that the previous question could be important. But of course, the previous question is a very difficult one, okay? So we want to limit ourselves to a more simpler question. There's the following. Given some Birkhoff section associated with some Anosov flow phi m, can we decide if the flow is equivalent to a suspension Anosov flow just by looking at the information associated with the Birkhoff section? Well, so in the next talk, we we will say something about this problem. We'll be able to traduce this question into another question that involves singular affine structures on surfaces. But before before finishing this first part, we want to introduce another technique that is very important in the construction of Anosov flows in three-dimensional manifolds. It is called the Fried surgery. Well, so what's Fried surgery? The Fried surgery is a kind of dense surgery, but adapted to the pairs flow and free manifold having periodic orbits. So consider some flow phi t, some Anosov flow phi t in a three manifold M, and take some periodic orbit gamma. Here in this figure, we imagine that the top and the bottom of the figure are glued together, so this represents a closed orbit of the flow phi t. Well, so consider some local transverse disk for this periodic orbit and some small tubular neighborhood, and make the blow up of the three manifold along the periodic orbit. There is, for each transverse disk like this one, we will replace the middle point by a whole circle. Okay. Um, so we can produce, making this operation, a new three manifold with boundary, with one boundary component, and we can lift the flow phi t and produce a flow phi t star in this three manifold. Observe that near the boundary, this blow up operation is nothing but a circle bundle map from the boundary of M star onto gamma. Okay, and if we collapse here each meridian direction determined by this annulus here, well, collapsing these meridian directions produce the orbit gamma. Once we have this flow, consider now some closed curve sigma contained in the boundary, and consider um, a foliation, a whole foliation of the boundary of these three manifold by closed curves parallel with sigma, and make the quotient of this two-dimensional torus by these closed curves. Well, if the foliation by curves parallel to sigma is well chosen, we will produce here a new closed three-manifold equipped with a non-singular flow Ct in N. Okay, and this helicoid-like surface here on the right is the result of the original disk that we have on the left. So after blowing up and then blowing up in a non-trivial way, this disk is transformed into this kind of local Birkhoff section around the periodic orbit. This surgery can be applied in the family of Anosov flows, but can be more general. It can be applied on any flow having one periodic orbit. And there are some technical issues with this construction. There are some technical issues. So in particular, in the case of Anosov flows, one question is to understand if this surgery transforms anosov flows into anosov flows, or flows which are equivalent with anosov. Mm, and well, it is not obvious the answer, but the answer is yes. The answer is yes. If the answer is yes, if we are in the class of transitive anosov flow. So for the case of transitive anosov flows, we start with such a flow, we make Fried surgeries, and we obtain transitive anosov flows. And one last remark is about Fried surgeries on suspension anosov flow. I want to make the following remark. So consider a suspension anosov flow. Here in the figure on the left, we have, well, this represents a torus T2 times an interval where the top and the bottom are glued together using some Anosov matrix A. So this is, it represents a suspension Anosov flow. And in this suspension Anosov flow, we have some global transverse section that we call T, and it's shaded in green. Well, assume that there is some set of periodic orbits and integer numbers here, some finite set, such that if we make Fried surgeries along this finite set of periodic orbits with the indicated integer parameters, we obtain another flow, another flow. Well, assume that the new flow is as well a suspension. In this case, the global transverse section T will be transformed into some Birkhoff section. So some Birkhoff section that I will call it T hat, T tilde, okay. And if the flow on the right is as well a suspension flow, it has a global transverse section that we call sigma. Well, when we make the surgery on the inverse sense and we come back to the original flow, this surface sigma transforms into a Birkhoff section sigma here, say sigma tilde for the original flow. And the boundary of this Birkhoff section is exactly the set of periodic orbits that we originally used to make the surgery. And observe that since the genus of this surface is 1, then as well the genus of sigma tilde is 1. So the remark is that a free surgery on a suspension Anosov flow will produce another suspension Anosov flow if and only if there exists a genus 1 Birkhoff section um, whose boundary coincides uh, with the surgery locus. I mean with the orbits that we use for making the surgery. Thank you very much.